Hi all, in the last class we have discussed the propagation of longitudinal wave in rod. So today we are going to discuss longitudinal wave in gases. So what we'll basically do is we'll derive the expression for propagation of longitudinal wave in gas, and finally we'll find out the expression for the speed of the wave, the speed of longitudinal wave in gas. Okay, so the derivation is actually similar to our the previous derivation. So previously we have discussed this case, that is longitudinal wave in a rod. Okay, so we have almost the similar derivation, but there are some slight changes because since we have moved from the solid to gas, the modulus of elasticity cannot be Young's modulus, so we have to introduce the bulk modulus instead. Okay, so the situation is similar. So consider some propagation of wave through gas. Okay, now let the plane A and B represent two planes in gas. Let A and B represents two equilibrium equilibrium positions of two planes in gaseous medium. Okay, so then when wave propagates, the particles at the location A would oscillate, as well as the particle in the location B would also oscillate. So after some time, the A prime and B prime would be the location of planes. Okay, so then as we have represented earlier, the initial separation between A and B represents delta x, and the separation after some instant, that is during the oscillation, the separation between A prime and B prime represent as delta x plus delta y. And since small a represents the area, okay, so therefore what we can introduce here is we can introduce the change in volume. So in case of rod, we are interested in the change in length, whereas in case of gas we will be interested in the change in volume. So the change in volume within the plane during oscillation. Okay, so what is the change in volume? So we can find the final volume. The final volume between the A prime and B prime can be written as A times delta x plus delta y minus the initial volume is A times delta x. Therefore, the change in volume can be written as A times delta y. Okay, so since we have found out that the change in volume, so it is very easy to find the volume strain. Therefore, the volume strain, by definition, it is the change in volume divided by original volume. The change in volume is A times delta y, and the original volume, that is the original volume within A and B, it is A times delta x. So that would be delta y by delta x. Okay, so when delta x tend to 0, so if the separation between A and B is very small, then volume strain can be written as dy by dx. Okay, so next we can go for the definition of the bulk modulus. So the bulk modulus defined by the symbol E is equal to volume stress divided by volume strain. Volume stress is nothing but pressure, and the volume strain is dy by dx. Now we have to put an additional negative sign here, because if you apply the pressure, the volume decreases. So the change in volume would be negative, or the volume strain would be negative, but the bulk modulus should be positive. So in order to overcome that negative sign, so better put a negative sign in this definition. Okay, because if P is positive, dy by dx would be negative, the total quantity E would become positive. So hence the expression for pressure can be written as minus E times dy by dx. Okay. So since this is a pressure, then what would be the variation pressure? Delta P. So the variation pressure through this gas, this can be written as dP by dx times delta x. Okay. So since we know the change in pressure, we can easily find out the expression for force. Force on the segment AB. So the force is equal to area into the change in pressure. That would be equal to A into dP by dx times delta x. Is equal to A into what would be dP by dx? This will become minus E d square y by dx square times delta x. So therefore the force on the segment AB can be as minus E A delta x d square y by dx square. Okay, now we can use the Newton's second law. The force on the segment AB would be equal to the mass into acceleration. So the mass of the segment we can represent by symbol delta m. And the acceleration can be d square y by dt square. So since the force decreases the displacement, we can put a negative sign here, and therefore it's minus, and that this small segment, the mass of this small segment can be as rho times A times delta x times d square y by dt square. Now equate both the terms, both the right hand side terms. That is equation number 1 and equation number 2. So if you equate the RHS of 1 and 2, you get minus E A delta x d square y by dx square is equal to minus rho A delta x d square y by dt square. So delta x cancels, E cancels, sorry, A cancels, rho, okay, rho does not cancel, negative cancels. So finally d square y by dx square is equal to rho by E d square y by dt square. So this is nothing but the wave equation, and hence this quantity, this rho by E, would be equal to 1 by v square, or v equal to square root of E by rho. Again, E is bulk modulus and rho is density. So the expression for longitudinal wave in gas, it is similar to the expression for longitudinal wave in the rod. So only the difference is, instead of Young's modulus, we got the bulk modulus. Okay. So next we can find out This the speed of the wave or the speed of sound wave in air. Okay, so we can find out the speed of sound in air as v equal to square root of e by rho, where e is called the bulk modulus. Okay, so the bulk modulus by definition, which is equal to minus v dp by dv. So how we are getting this? Okay, because we know that is equal to stress by strain. The stress is the change in pressure. The strain is the change in volume by origin volume, and therefore it is equal to minus v dp by dv. Okay. Now the propagation of the sound in air is proposed to be an isothermal process. So okay, so there are two model for the propagation of to explain the propagation of sound in air. So this isothermal process idea is introduced by Newton, and there is another theory as well. It is introduced by Laplace. Says that the propagation of sound in gas is an adiabatic process. This was introduced by Laplace. Okay, so you might be knowing what is done by isothermal process and adiabatic process as well, because you already studied +1 in +1 in thermodynamics. There is a discussion about the isothermal process and adiabatic process. So isothermal process means the process in which the temperature remains constant. So the isothermal process, the equation would be P times V is a constant because temperature is a constant. And in adiabatic process, the equation is PV raised to gamma is a constant. Okay, and where is gamma? Gamma is Cp by Cv, the specific capacity at constant pressure divided by specific capacity at constant volume. Okay, so the original idea, the initial idea is given by Newton. The Newton proposed that the propagation of sound must be through an isothermal process, and he tried to derive the expression for speed. Okay, so practically we already know what is the speed of sound in air, and the speed of sound is found to be approximately 330 meter per second. Okay, so if we are getting 330 meter per second by using this expression, that means your theory is correct. Okay, so first we can check the Newton's idea. So Newton's approach, this an isothermal process. Okay, so according to Newton's idea, this P times V is a constant. So therefore P times dV plus V times dP must be 0. Just differentiate it. So just differentiating on both sides, differential of PV equal to 0, so that we can write as d of PV. Okay, so from this we can find out the expression like this. So P dV equal to minus V dP, or P is equal to minus V dP by dV. Okay, so therefore the modulus of elasticity, or the bulk modulus E, which is minus V dP by dV, is simply equal to pressure. So if for an isothermal process, if the process is isothermal, then the bulk modulus of the gas is simply equal to the pressure itself. So therefore, the speed of sound is equal to square root of E by rho, and it is equal to square root of P by rho. Now we can substitute the values for the pressure and the density. So at standard temperature and pressure, so at standard temperature and pressure, what is the density of gas and what is the pressure? So pressure is 1 atmospheric is equal to 0.7613800 times 9.8 Newton per meter square, and density of gas is 1.293 kilogram per meter cube. And if you substitute this value, then the velocity of sound is equal to square root of P by rho will be approximately equal to 280 meter per second. So it is less than 330 meter per second. So that means there is a small inconsistency in the Newton's approach. So although it is getting very close to 330, but we are not getting the exact value. So we may not be able to consider the propagation of sound is an isothermal process. So then next we can check the Laplace's approach. So in Laplace's approach, the propagation of sound is an adiabatic process in which PV raised to gamma is a constant. Okay, so then again, the differential of PV raised to gamma would be 0. So this implies that gamma times P, so you can do the steps, equal to minus V dP by dV. Okay, so I've just steps. So what is the steps here? So it will be P times differential of V raised to gamma. This is V times V raised to gamma times V raised to gamma minus 1 plus gamma minus 1 times dV plus dP times V raised to gamma equal to 0. So just rearrange it and we can find gamma times P equal to minus V dP by dV. So therefore the modulus of elasticity or the bulk modulus is gamma times P, and the gamma is 1.4 for air. Okay, so then finally, what is the speed of sound? So theoretically, it would be equal to square root of gamma P by rho is equal to square root of 1.4 times 280 meter per second, and which is approximately equal to 332.5 meter per second. So it's very close to the speed of sound. Okay, so it is a perfect match with the experiment. So hence the Laplace approach might be correct approach. So therefore we can consider the propagation of sound in air is an adiabatic process rather an isothermal process. Yes, we can conclude that the propagation of sound in air is an adiabatic process and its expression is V equal to square root of gamma P by road. Okay, so that's all about the propagation of longitudinal wave and as well as the propagation of sound in air. So now the only topic remaining is a stationary wave, so that we will discuss in next class. Thanks for watching. See you.